Okay, so we are doing the homework questions from Chem 101 for Bohr model, quantum theory, or quantum mechanics, and periodic properties. So this first question is calculate the energy in joules of a single photon of blue light with a frequency of 7.5 times 10 to the 4th hertz. So remember, this is frequency, right, which is frequency. So frequency is 7.5 times 10 to the 14 hertz. And remember, hertz is the same thing as an inverse second, right? And so we want energy. So we need energy equals h nu, right, which is supposed to look like this. And so energy equals, they give us h, 6.626 times 10 to the negative 34 joule seconds times 7.5 times 10 to the 14th inverse seconds, which is like 1 over second. So you can see here the seconds will cross off. And when we do that, we get 4.97 times 10 to the negative 19th joules. So just as a reference, this is talking about sunlight. So visible light is always 10 to the 19th, that exponent is always 10 to the negative 19th with energy of visible light. So that's like a nice little thing as like, oh, okay, yeah, right, I did this correctly. So make sure you put this in your calculator to make sure that you're getting these correct numbers. Otherwise, you're just putting something in your calculator wrong. So send me a picture of your calculator when you're doing the calculations, and I can help you with that. Okay, here's the next one, and I got this one from a lot of people. So for a hydrogen atom, calculate the energy of a photon that would be emitted for the orbital transition of n equals 5 to n equals 1. Now, with all these Chem 101 questions, you might not be getting the exact same numbers as I have. Like, so yours might have been like 4 to 2 or something of that sort, but everybody gets a little bit different numbers. So I chose this equation. Remember in lecture we did, I think, 3 different equations that could get you to this answer. I just like this one because it's the shortest, honestly, hence why I use it. So the key here is you have to remember, when you get this lambda, you have to take your answer and raise it to the negative 1, or you're getting 1 over your answer. So this is the most important piece. I always tell people, don't try to like rearrange this because that's just crazy. Just leave it 1 over and don't forget to raise your answer to negative 1. Okay, so let's do this. So you have 1 over lambda equals r. And so 1 over... So our final, oops, wait, where'd it go? 1 over 1 squared, because initial was 5 and final was 1, minus, so our final is 1, our initial is 5, 1 over 5 squared. And then r is given to us here. And again, you could have used an equation that didn't use this r, but you also could have. I showed you a different one in class that you could have done, but I like this one. And so it's 1 over, well, I guess it's just 1 minus 1 over 25, right? 5 squared. And I got, in my calculator, okay, so I got 9.524 times, oh wait, that was after I raised it to the negative 1. So this remembers 1 over lambda, 1 over lambda. So I got, okay, 10,000 or 10,529,088. Okay, this is not correct. I have to raise this to the negative 1. When you raise it to the negative 1, then you get 9.524 times 10 to the negative 8th, right? And this is our lambda, right? But that's the wavelength. They want energy. Well, energy equals h nu, but remember what's nu? C over lambda. So I can just plug this in here. And for your quiz, I gave you these two, but I did not give you the combined one. I'm going to do the same thing for your exam, FYI. hc over lambda. So I just plug this in. So E equals, so h is 6.626 times 10 to the negative 34th. This is a constant, always given to you. and it's joule seconds. C is the speed of light. It is also a constant. Oops, positive 8. It'll always be given to you. Over our lambda, which is 9.524 times 10 to the negative 8. And this is meters. So you can see meters, meters, seconds, seconds, and you end up with your joules, which is 2.092 times 10 to the negative 18 joules. And technically for this one, so those of you who are like rocking good at math, if you didn't raise it to the negative 1, you could have just put it right here, right? Because then it would have been on the top, and that would have worked too. But I like to stick with my equations, so I rearranged it. And then sig figs for this one you don't really have to worry about because this is a constant, so we wouldn't use it. And this is right, these are certain numbers, right? So they have infinite sig figs. So really you could have been pretty flexible on these sig figs. Okay, let's look at the next one. Ooh, quantum numbers. Okay, so for these quantum numbers, we have to remember energy level, sublevel, orbital, energy level, sublevel, orbital, spin, S. Okay, I'm going to put this SPDF. I don't know if I'll do it on every single one of these problems because it's probably going to get annoying, but maybe we'll see. So the question says, how many electrons in an atom can have the following quantum numbers? So n equals 4, that's the fourth energy level, right? L equals 2, remember, L equals 0, that's an S sublevel. L equals 1, that's a P. L equals 2, that is a D. So here we are. Remember, this is 3D, so we're somewhere here, right? And m sub L equals 2, so remember m sub L, it's going to be negative L to plus L, right? So that's negative 2, negative 1, 0, positive 1, positive 2. So we're saying it's in this one. All right, so we're in m sub L, negative 2, and we have plus S. So we're at plus 1/2. So the question is this kind of a trick question. This one says, how many electrons can have the following quantum numbers? Only one. There can only be one electron that is in n equals 4, L equals 2. And so if we want to try and use the periodic table, so if we call this like, negative 2, negative 1, it doesn't quite work with this way, we know, because it goes up, 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 then down, 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 right? Hund's rule. Plus 1, plus 2. So that means we're in this one. And so if this one is up, that would be plus 1/2, right? Well, no other electron can be up. The other one will be over here and be going down. So the answer is 1, right? No two electrons can have the same 4 quantum numbers, right? So Pauli exclusion principle says that each electron has to have a unique set of quantum numbers, right? So no two electrons can have the same quantum numbers. That was kind of a tricky one. Okay, next one. Oh, sorry, you can't quite see all this, but I think you can see most of it. So a single electron in an orbital has quantum numbers n equals 3, L equals 0, so that's S, P, D. Remember, here's L equals 0 is S, so we're here in the 3S. M sub L equals 0, and M sub S is negative 1/2. Okay, so that means we're here in the 3S. So here we are, we're in the 3S orbital. So negative 1/2 usually means going down. So the question is, what are the quantum numbers for the next electron? So if this is going down, and it says that it's a single electron in this orbital. So it's saying there's one electron in this orbital. Well, orbitals can have 2 electrons, can't they? So if this one is negative 1/2, then that one is, we call this spin down, negative 1/2. This one is spin up, plus 1/2. So this means we could have 2 electrons in this orbital. So that's n equals 3, L equals 0. And then if L is 0, M sub L is 0, right? So M sub L is 0 because that's the only possible values. And then instead of negative 1/2, it's plus 1/2. So that is where the next electron would go. Again, the key was it said there was only a single electron in that orbital, which means we could add another electron. And if this one's going down, then this one must be going up. Okay, another one. Ooh, look. I feel like this one is exactly the same. Yeah, look at it's like literally almost the exact same question. Almost the same. So very similar, so very little difference here. So n equals 3. Oh, but this time L is 1. So remember, L equals 0 is S. L equals 1 is P. So now we're in the 3P over here, right? S. We're in the 3P. Okay. M sub L is 0. So remember, if L equals 1, M sub L can be negative L to plus L. So that means negative 1, 0, positive 1, right? So negative 1, 0, positive 1. So we're somewhere in one of these P's here. It says we're in 0. Okay, so, and it says a single electron is in the subshell. Okay, so if there's a single electron in the subshell, I have a couple options here. Draw these 3 as orbitals. So 1, 2, 3. And so this would be like negative 1, 0, positive 1. So think of it as like that's like px, py, pz. And so this one says there's 1 electron in here. So technically, the next electron could go over here, which would be m sub L equals negative 1. Or the electron could go over here, which would be m sub L equals positive 1. So both of those are an option. So if we put it over here in negative 1, so then we would have n equals 3, because it's still the third energy level. We're still over in P, so L equals 1. And then let's say it goes here. Okay, so m sub L equals negative 1. And now it could go up, which would be m sub L equals plus 1/2, or it could go down, which could be minus 1/2. You kind of get to pick on this one. So we get to pick with this one. When I did this one, I chose these. But there's a few options. You also could have chosen this as a plus 1. It could have gone in any of these because these 3 are degenerate, meaning they have equal energy. So here's where we knew it was. It could have gone over here to plus 1 and plus 1/2. Could have gone here to plus m sub L is plus 1 and m sub S is negative 1/2. Could have gone here where m sub L is negative 1 and m sub S is negative 1/2. It's a couple different places you could have put this electron. That would have been correct. Okay, electron configurations. So silver is here. So S, P, D. Again, you can have this written on your periodic table. 3D, 4D. All right. Oh, this one's a long one. See, we just read it as we go across. And remember, P just keeps going like this. So we just read. So 1s2, 2s2. I'm just counting the boxes as you go across. We're still in 2. Now we're P, 2p6. You're in 3s, 3s2. We're still in 3. This is P, 3p6. 4s2. This is 3d. Remember, d starts at 3. 3d. 10. Stop there. Back to 4 again. 4p6. 5. Here we are in S. 2. Oh, but this is silver. So we think it's 5s2, 5s2, 4d. 1, 2, 3, 4, 6, 49. Remember, silver is an exception, right? Our exceptions are the D4s and the D9s. Now again, exceptions to our rules. So remember, we did this one in lecture. So if I drew this D out, it goes up, 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 down, 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 and here's our S, up, down, right? So what happens is it steals, here's our 5S, here's our 4D, it steals it. And it's like, aha, now we get to be full. So it actually is 5s1 4d10. Because remember, electrons will be empty, half full. If they can. Like, that's not always an option. But if it's close, they're going to do it. And so the exceptions that do that, again, are the d4s and the d9s. And I'm okay with you putting these exceptions. You can't write the whole thing out, but you can write something to help you remember that it's an exception to the rule. That's totally fine. Okay. Now this is an ion. This means, because it's positive, that it's lost 2 electrons. Just really quickly, let's just do the abbreviated one of this one. So how can you do the abbreviated ones just so you can see it? Just because this is, you don't need to do this for Chem 101, but it's just really good to do and know and understand because it makes our life easier later. So we have silver. So you go and you look at the noble gas before it. So the noble gas before it is krypton. Also, what you can do is you look for the P6. And if you look, here's 4P6. That's krypton. So all of this is krypton. And then you just bring the rest down. 5s1, 4d10. So that's the abbreviated way. And it's always the noble gas before it. So always look for that P6. That's the noble gas before it. Okay, now this one is an ion. So here's manganese, not an exception to our rule. Okay, so we gotta do this again. SPD. We gotta write the complete, no cheater pants, we can't do the abbreviation. So we gotta do the whole thing. So okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, it's not a 4. Remember, this is 3. 3d, 1, 2, 3, 4, 5. Now this is the manganese atom. Remember, atoms have the same number of protons and protons and electrons, right? This says we lost 2 electrons. So remember, they always lose from the outermost energy level to in. Or even though this is from low energy to high energy, that's the way the periodic table is written, from low energy to high energy. It's not written in distance from the nucleus. It's written from low energy to high energy. So 4 is further away from the nucleus than 3 is, right? So all transition metals lose the 4 or the S's first. So manganese 2 plus will be 1s2, 2s2, 2p6, 3s2, 3p6. It's going to lose the S's first why? Because 4 is bigger than 3, which means it's further away from the nucleus. So it always loses the outermost energy level first, and there's 2 plus, and there's 2 of these electrons, so it loses both of them. So this is the electron configuration for manganese 2 plus. Right, next one. Oh man, the complete one for mercury. That's a big one. Here's mercury. Oh, we need our F's. Hold on a second. Let me fix this periodic table. Mercury. So here's S, P, D, F, right? 1, 2, 3, 4. Our energy levels. Here's 3, 4D, 5D, 6D. And remember, F starts with 4. F. So we're going here. So this will be a long one. So important to know, do you see how this one goes from 57 to 72? Well, here's 58. So it means we have to go down here all the way over. Here's 71, here's 72, then we go back up here. So usually when people get this one wrong, it's because they miss this jump. We got to go from 57 down to here. All right, so I'm going to go fast until I get down to like the D's, okay? So 1s2, 2s2, because we've done this like, I don't know how many times now, 3s2, 3s2, 3p6, 4s2, so here we are, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and here we are now. Before we get to this D, right, we got to go down here. This periodic table is not the best one. The one that you have is a little bit better. Sometimes they leave this an empty blank. But so we go from 6s2, then we go down to 4f14. If you count across, it should be 14 boxes. And then you come back to Mercury, and that is a mess. 5d10. So if you got this one wrong, it's because you forgot to go to F, right? It's because there's jump here. And again, it depends on your periodic table. So some have the jump right here, which it should be. The one I chose, unfortunately, has the jump in the next place. But the one you have has it in the correct place, the one that you have for your quizzes and exams. Oh, thankfully, condensed. Ah, yes, arsenic, easy peasy. Okay. An easy way to do this, you can draw out the whole electron configuration. Absolutely, you can do that. Or you can just look at the noble gas before it. And then go 1, 2, 3. This is 3p6, which is argon. And you just do that. And then you just keep going from there. So 4s2, 3d10, 4p3. Ah, condensed structures. So lovely. So yeah, just look at the noble gas before it, and then you just keep going, right? Your SPD, and then you just keep going with your electron configuration. Okay, these ones are fun. So there's a couple different ways you can do these ionization energies. So here's the choices. So this is a multiple choice, and these are the choices they gave us. So Na, Mg, Al, Si. So what you're looking for is you're looking for where's the biggest transition, right? So like where's the, so this one's like 600 to 2000, that's not that bad. It's like 2000 to like 3000, not that bad. Oh, look at this one. It's like, whoa, that's huge. And then this one, that's not that big. So this is the transition, right? And so when this happens, so this is the first electron. This is the second electron, right? This is the first ionization energy, second ionization energy. Here's the third ionization energy, fourth ionization energy, fifth ionization energy. So something happened. This was a very happy third ionization energy, right? And then it was like, no, don't take it. When you see this huge jump, that means we went from a valence electron to a core electron. We don't want to take away cores. So for sodium, sodium is right here. It only loses one electron, and then it's at neon. So neon, this is when the core electrons are, right? This is P6. And I did this a little bit different in lecture where I actually drew out all the electron configurations. You can totally do that. This time, I'm just going to use the periodic table. So the jump in sodium would be from between the first and the second. Because when it loses one electron, here it is, happy camper after one electron. So it's definitely not sodium. Let's look at magnesium. So magnesium loses 1 and then 2. So its big jump would be between 2 and 3 because it's when you're trying to take this electron away. Nope, this jump wasn't between 2 and 3. So aluminum. So aluminum, here we go. We lost first electron, second electron, third electron. We're here at neon. So it would be between the third and the fourth. Oh, look at this one. This one's between the third and the fourth. This must be aluminum. So if we look at silicon, let's just do silicon real quick. So silicon loses 1 electron, 2 electrons, 3 electrons, 4 electrons here. So it would be when you took this electron would be away. So it would be between the 4th and 5th for silicon. And for phosphorus, if we did phosphorus, 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons. So at 5 electrons it would be here. So the jump would be between the 5th and the 6th, because remember, it's when we're removing this one. So this one is aluminum. And you can also draw out the electron configurations, but you can also just do what I did using the periodic table. The jump comes when it tries to take it away from the core. The core is after it's become a noble gas. Okay. Last one I got. Which one of these statements is true? So, that's not written very well, is it? So I'm just going to do Na. Just make it so it's all one line. Na plus gas plus E minus. Okay, so, sorry, I always circle my electrons like that. So what's happening is we're losing an electron. And we're going from an atom to an ion. Okay, so, let's see here. Let's just go through. The electron required is electron affinity. I mean, I don't know, maybe. Go back that one. Exothermic. I don't know, maybe. Na plus is an anion. No, that's definitely an anion. This is an ionization process. Maybe. Okay, so we just got one that we know definitely not right, right? So electron affinity, right? Electron affinity is the energy it takes when you gain an electron, right? This is from gaining an electron. Gotta know your definitions. Well, we're losing electrons, so give me that one. Exothermic. Exothermic means heat is produced. I don't see anything about heat here. So I don't know how we could draw that conclusion. There's nothing about heat, right? This means heat is produced. Well, something about heat. Okay, so let's do ionization. So ionization means becoming an ion. Well, look, we're an atom, and we became an ion. Aha, I would choose this one. It's becoming an anion. It's becoming a cation, right? So an ionization just means becoming an ion. And so this is indeed an ionization process. Okay, so hopefully that helps going through some of your Chem 101 questions. A lot of them are very similar to this. I got a couple other questions, but they were almost exactly identical to these. So hopefully this really helps you with your homework and also helps you with your quiz that's coming up this week. If you have any questions, send me a text and I will get back to you as soon as possible. Have a great day, everyone.